Oh, ugly.
Or
Yes.
more bubble. More of our bubble.
Yes, bubble, but
It's plus one.
tell me more. I'm just lazy to speak. If you please.
Is it the different states?
Oh, it's like two matrices. Are these matrices or just
Sort
they
of.
just happen to have the brackets?
Well,
Well,
One
the
minute.
derivative of the states, so it's the.
Yeah, the derivative of the states is the.
Yeah, the density of states, so it's the density of states.
no.
Oh,
By the way, you thank you everyone for submitting homeworks in time. For verbal explanation of density of state was perfect, but visually one may plan to add equations when some definitions are required. I'm flexible and don't care, but like if you would do this
like for Dr. Parent.
whatever, yeah. So sometimes in the mathematical intense course, the definition means just write an equation.
Fair enough.
What are C1 and C2? You already started telling something.
That's the different states. So like the first state and the second state, right?
Yes, but they are not bra or cap. They do not have dependence on x. They are not wave functions. It's like a scalar depending on time. So whatever. You are likely, most likely, 99.99% correct, but I am looking for a terminology. Like there is an abstract quantum state. There is a quantum state in a continuous wave function representation. There is a representation of wave function as an expansion over a basis set with some expansion coefficients, proportions, how certain basis state enters into overall quantum state. And when you were like a couple of hours ago, you were looking at that superposition of ground and excited state of the particle in the box with a 50% distribution. And this 50-50 was what? How would you call it? Like if you're looking on not an eigenstate, if you look at quantum state of some quantum system, let's say particle in the box, we do know the ground state, first excited state, maybe other states, and we intentionally prepare initial state, which is neither ground nor excited by, but like superposition of them with proportions like 50-50. What are these 50-50 numbers? Which terminology will be used to speak more general about it? Like percentages, proportions, right? But something more quantum or more mathematical is flying in the air and we need to catch it.
Constants.
Constants if they do not change in time. But if they eventually may change in time, then so there are basis functions, right? We bring them together with certain proportions, with certain proportionality or yes,
That's the 1 over.
expansion coefficients. We expand. Okay, and in things that you did before, expansion coefficients were constants, and therefore you use the word because in many situations they do not change over time. So it was 50-50 proportion for all the times. But there are situations when this expansion coefficients, when this proportions change. For example, example when a quantum system is changing from ground to excited, or when it was 50-50 and then it changes completely excited or completely de-excited. You are giving these examples. Just I admit I'm guilty of shocking you of unexpected questions, but the answers are in your head. In your heads.
We just have to find them.
Yeah, because this is like what Yulin was talking about at lab.
Yeah.
Maybe I should admit I didn't watch it like each minute. I just
That's okay.
Yeah.
fast forward, looking that it was more or less friendly.
Dash.
Cashew.
Oh, right.
Man,
Cashews.
I like cashew.
I just
Are
offered
you
them.
offering my cashews?
Oh, no.
They just made me think of it.
So what is the reason for quantum states, for systems, for molecules to be excited in the excited state?
Is it, does it have like an increase in
They're,
energy?
yeah. They're excited.
Yeah, we are all
They
excited.
increase their energy, the energy level.
Yes, if I pursue my dream of bringing quantum chemistry to 3 and 4 years kindergarten kids, to symbolize an excited, I should draw like a symbolic human, like ground state, laying on sofa, excited, jumping and lifting hands.
Yes.
I'm so excited. But what does excite a molecule, not a human? We all have an idea how to excite a human, but how to excite a molecule. So
Like any sort of energy.
Like light or something.
Yeah.
yes,
Oh,
they like it. They like it very, very much. So light, electromagnetic radiation. If it is NMR, it is radio frequency NMR that flips the spin. If it is optical, it is like light quantum that excites a molecule. If it is infrared, then it is like infrared radiation. Okay. And if our molecule is being subject to electromagnetic radiation, then expansion coefficients may change over time. Therefore, generally, we may keep them as time dependent. Although in the vast majority of the examples considered in this class, they're constant, but it is not so general. Okay. In all undergraduate physical chemistry quantum classes, the wave functions are treated as differentiable functions for calculus differential equations, right? Continuous distributions. But you do know that because of the whole hierarchy, one can also speak of a quantum state as a vector. Right? Or at least no one throws rotten tomatoes on me while saying this, which means like no one is against, it means that everyone is for it.
Yep.
Democracy in science. Everything accepted by majority of votes is considered true.
Yeah.
Okay. So suppose that we are professional theoreticians, professional quantum chemists, or maybe it's too boring for all of us. Suppose you all are directors of research centers, and each of you have hundreds of theoretical quantum physical chemists in your subordination.
Nice.
Okay. And you need to give them the right tasks. You need to assess their productivity. You need to send reports to federal agencies, pull more money, feed your staff.
Yeah.
And then, therefore, you are interested to make them as efficient as possible. So if you take our undergraduate philosophy approach with continuous functions, you solve differential equations. you make like numerical solution in this infinite number of dimensions. They will do something, but your institute will be not productive because there are no so productive computers, there are no so productive humans. So this continuous functions are mathematically challenging, and if numerically represented, there are too many degrees of freedom. Especially if any true problem is not one-dimensional, but three-dimensional, or if there are more than one, then 6-dimensional, 9-dimensional, blah, 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 blah. Right? So to be and then your institute sucks, and you cannot You can get federal funding to feed them, and
Yeah.
you need to find something creative. So there is a common trick which is so basic, so trivial and self-evident that people do not call it a trick, and even skip it. And I wasn't attending. You all are so much better student than I was at my undergraduate times. In my best time, I attended maybe 50% of meetings, probably less. And maybe the idea that we are going to communicate today was delivered at a time when I was just out of the class, like Sam and Melody today.
Yeah.
Or it was assumed so self-evident that no one cared about, like, our instructor considered it to be a natural thing. But I saw a barrier, like abstract intellectual barrier in getting this theory for like next few years. And will try to overcome it and like invite you to through a shortcut that you will feel more comfortable. And so it doesn't give you mathematical derivations, it's more ideas. So here is the idea for you as directors of institute. Continuous functions are bad. They soak effort and they give no output. They would only to torture undergrads. For practical research, they are no good. But if we accept the idea of basis functions and expansion coefficients, we will fly like eagles.
Yes.
So each function can be considered as a summation of few basis functions with discrete expansion coefficients. If you already know predetermined basis functions, then instead of like 1,000 or million or like 10 to the power 46 degrees of freedom, we have just handful of expansion coefficients. You write equations for them, and your institutes will be so productive, you will beat other institutes. So through the concept of expansion coefficients in certain bases, one can boost production by several orders of magnitude. And those C1, C2 are expansion coefficients. Typically, there are more than two, but to get the idea, we do not need more. Okay. So what we do see on the board is the analog of time-dependent Schrödinger equation in a certain basis. So instead of dealing with wave function, we deal with vector of expansion coefficients and a matrix of Hamiltonian. So Hamiltonian, which was originally expressed as a differential operator, now is expressed as a matrix. And the major goal of our today's meeting is to, well, we need nothing except this equation, but we need to come in peace with this equation and with our peace of mind to accept it, to get an idea of what it is. So what are the elements of this Hamiltonian matrix? How will we call them?
Well, you got your Hamiltonian operators and the H hat, or is that and the, or it'd be I over H hat, right?
Mm-hmm.
Then, yeah, so you just have your operators and then your like imaginary part. I guess.
But see, there is the H, and then there are these angular things. Is one, 2.
Yeah.
So
Is
what?
that-
Yeah,
It has
okay.
to do with like the different energy states between like its initial and final state.
He is very correct. He told us everything except the terminology, which is very silly, stupid, and they do not like it, but everyone else in the world accept it. So I need to follow the majority. So these things that Fred did define I cannot repeat. He did it much better than I ever could. So operator, then how do you call this? Energy states multiplied, getting a number.
Okay.
So from the differential operator, we get a matrix. Matrix consists of elements. If this is a matrix consisting of elements, then those are called matrix elements. Kind of makes sense, but I hate it.
Okay.
I still hate it, but I was especially hating when I was not understanding why we need it. So this idea that we all agree on now was like darkness from my last like 2 years of my undergrad. And I was like, show me a person who designed this one.
Yeah.
Okay. So
It's at least one equation.
yes, it's our favorite thing.
It's our.
How you got to start?
Yeah.
And let's share the screen. Oh, I successfully wasted half an hour. I gave myself zero time to the right things on the blackboard. So we need to rush through.
I got it.
So what are the 1 and 2 symbols with this angular brackets?
What?
What are 1 and 2? You see there are angular brackets, right? H, and there is a 1H1 with this angular things. What is 1?
What state? Like grab state.
Yeah. Oh yes, yes, yes. I'm excited, man. Okay, what is 2H2? What is 2? Excited state. Okay, and if we have 1H2, what is this?
That one, I asked Yulin if it was representing the wave function, like going from the ground to excited state. Is it? Oh,
Exactly.
straight answer. Yeah.
Transition.
Couldn't tell if it was right or not.
So matrix element of a transition from state 1 to state 2.
Okay.
Yes, it is going from state 1 to state 2, or from if like there is like from 2 to 1, or here it goes from 1 to 2, right? And this matrix elements, and if you have like I, H, J, where I is I, and same with J, integral I star H I J dr, right? Matrix element. So matrix elements are needed for time-dependent Schrodinger equation in matrix form, in this finite differences, and it also needed, as we remember from your presentations on postulates of quantum mechanics. You do remember to find outcome of the measurement, to find the expectation value of observable. You put it's the same thing. You put like average value of observation. You integrate your wave function. Start. You put here quantum operator of your observable wave function, and then you integrate it, right? So same idea. Just here we added indices. Okay. In some sense, we are done, but I have another 50 slides that I need just to jump through. So at the beginning and at the end, we have the same vector, right? Vector of this expansion coefficient. And the equation is equation of motion with constants and the matrix of matrix elements. of Hamiltonian, right? Okay. Bubble rules. Yeah, this is what I plugged into Bubble, and then it covered it. So, and some people do not like Dirac notation, and they just put indices on the bottom. It's acceptable. I have no idea what else. Maybe just community.
Summer something. Express.
Summation of known functions with some coefficients.
Okay.
I'm tired of reading myself. So here is like basis functions phi1, phi2, and expansion coefficients C1, C2, right? Transition from continuous to discrete. And then in our half-excited particle in the box, we have this one of square root, and then others are zeros. I think it was a couple of homeworks again behind, and the one for the Wednesday we also had problem like this. I apologize, but you need to refresh your mind. And please assign a few hours to try it. So it's, do not leave it for last night before submission. It's wonders are possible, but let's not count on them. Okay. Experiment, model, answer. Okay, it is a philosophy of science. Hamiltonian is time independent plus something time dependent. When you have electromagnetic radiation, it makes Hamiltonian time dependent. And then we have transition, and expansion coefficients are time dependent. What else? If we have bra times cat, it is row by column that gives normalization should be equal 1, right? So normalization can be expressed either in differential continuous functions or in this vectors. I think I'm not surprising you. You knew it, right? It is a serious flow chart diagram. It's not new idea. It's very trivial. So it's basically the idea of Dirac that either continuous functions or vectors can represent the same abstract concept. Here is an analogy to your idea. Come on. Postulates of quantum mechanics and the way to predict expectation value of the measurement. So here is what you have declared in the postulates, right? And if you want to express the same idea in the language of expansion coefficients, each can be expressed this way. So regular wave function is written as basis function 1, basis function 2, expansion coefficient 1, expansion coefficient 2. Conjugated bra instead of cat for function 1, bra for function 2, and then expansion coefficient star, expansion coefficient star. So this notation in this line, I'm not going to brag or request credit for it, but this is a bridge between linear algebra and calculus. So here we write in the calculus style, in just linear notation, the multiplication of a row vector by a matrix by a column vector. So it is just, if you have basis vectors and we pursue this Bryan cat notations, it is the same as multiplying vectors. And sometimes it gives benefit. You may practice it a few times more during the class. And if you look for the first term, so we open brackets, we have coefficient C1 star. Then from the second bracket, we have first element C1 without star. And then we have here matrix element of wave function 1 as a bra, wave function one as a cat and the operator between them. So it is how we come to the idea of matrix element. And if you apply this protocol to expectation values of observables, then we come to the same idea that Woon and David may have communicated to you. That if you need to predict an outcome of the measurement, you find matrix elements for time-independent functions once and forever, and then you, in your practical considerations, you only treat how the expansion coefficients change over time. So if there is no light, if there is no excitation, their absolute value stays constant. But even if Miltonian is time independent, they do accumulate quantum phase, right? I remember someone hated or was not very happy with the terminology accumulating phase.
Yeah, we didn't like it.
But now you accept it.
Yeah.
Accumulating phase means the absolute value is the same, but it oscillates in a complex plane depending on the value of energy, right? And then if these things are plugged into expansion coefficients, one can predict results of measurements at any point of time. But matrix elements, I'm just giving you a little heads up so that you do not hate your homework and myself too much this time, because the homework will be about computing matrix elements. So in some sense, we are preparing for this homework. Okay, same thing, just with a little better calligraphy. So result of measurement, all matrix elements, and then this combinations of expansion coefficients. So an operator which can be very differential can be represented by a matrix. And this is what a competitor of Schrödinger, what Werner Heisenberg was pursuing from his, I wouldn't say childhood, but as his major thing of scientific career. He never accepted only as a listener to Schrödinger, but in his personal research, he never accepted wave function. It was like, it's not, I do not know what is wave function, we cannot measure it. I believe only in matrix elements, and one should write equations only for them. And therefore, before majority of scientists agreed to follow Schrödinger, there were two competitive streams. The followers of Schrödinger were telling we are following wave mechanics, and followers of Heisenberg were telling we are following matrix mechanics, because the word quantum didn't exist. Okay, we are doing matrix mechanics. Oops, also sounds crazy. Okay, and here is the definition of matrix. Expectation value. There is another thing that I hope very much you did and David didn't use. So density matrix is combination of this expansion coefficients written as a matrix. It is a diagonal product cat times bra. And also I'm going to say how one can get the expectation value of an observable based on density matrix and matrix elements. To do so, one needs to admit mathematical procedure of trace. Trace means take diagonal elements and add them together. I make a bet that 5 minutes after class ends, everyone will forget this equation and never use it in the life. Unless you, instead of director of an institute of theoretical research, you become a researcher yourself. So if one multiplies density matrix times matrix of an operator that we need, and then take a trace, so one can practice it by doing row by column procedure. So 2 matrices, and then summation the trace. The answer here will be absolutely the same as we had a couple of slides before. So it will show the combination of expansion coefficients and matrix elements, providing an outcome of a measurement for the given wave function, or wave function represented through expansion coefficients at a given time. In some circumstances, density matrix can be more beneficial than wave function. In this class, we never need them, but just for your curiosity, if any, maybe not. If there is a dissipation, if the time is very long and the quantum system is not isolated anymore, it is perturbed by everything it sits on and it interacts with, density matrix becomes more general than wave function. And ask David Cropper. It's a major subject of his thesis. Okay. Now, the goal is to write Schrödinger equation in discrete basis. And here is a little plan. So good basis functions are expected to be orthogonal. So their bra times ket will be either 0 or 1. Not surprised. I'm doing my biggest pedagogical error by showing it as slides. So it is a waste of your time, waste of my time, because nothing shown on slides will be memorized. This, so basically, I pretend that I tell something, you pretend that you listen to something, and you forget about it. So, but I'll try to do better on next lectures and deliver things on the blackboard, because with very good relations, just objectively. I may try to do a quiz and observe that on Monday, all information from today will be gold. Okay, 5 minutes of pure pleasure. So here is the time-dependent Schrödinger equation that you always enjoyed, right? How wave function changes over time. So time derivative of a function depends on is driven by Hamiltonian. And this is something I wouldn't be surprised if you remember, because we derived it from the evolution operator, and then from this equation we can derive evolution operator. Right? By solving this differential equation formally, we get evolution operator. By differentiating the evolution operator, expanding in powers, we get the Schrödinger equation. That's how we do it. Now, the main trick of a director of an institute, instead of wave function, we practice expansion coefficients, right? Maybe it is the only thing to memorize from our today's meeting. So we are plugging 2 into 1. So as simple as 2 into 1. And then, as a poor undergraduate student in the past, I'm not expecting any derivations to be memorized or repeated. But maybe a little bit of logic can be picked up and then reused. So when we plug 2 into 1, it will be still an equation that includes basis functions. And our goal is to live without basis functions, is to remove them completely. Make sense? As you understand me as directors of institute. Mm-hmm. So we need to set up an equation where there will be no phi1, phi2 symbols. And we do have a tool to remove wave functions from anywhere. How many slides back should I go? So if we do have function, let's say 1, then we have function 2, we convolute them in this bracket dot product, we will get 0. So you'll get no wave function. If you have like phi2 and phi2, we convolute and we get 1. So it will be a number, not a wave function. So the orthogonality is designed by humans for humans. And the main reason for orthogonality to get rid of wave function. It's an instrument to remove wave function. So and it is in our plan. So you multiply by arbitrary number eigenfunction m from the left. And then it will be each term of the resulting equation will have Brian cat.
Hmm.
And when we Brian meets cat, wave functions disappear. You have either number or matrix element or just zero, nothing. And then we will get an equation for bosses or for directors of the institutes. Okay, I think this little
Cat?
well, cat Brian cat it's written from KET, not CAT. But since still a little tricks may launch memorization. So plug 2 into 1. So time derivative of the wave function equals Hamiltonian times wave function. Now multiplying by eigenstate number m from the left. So it is written here, but it is very poor calligraphy. I hope very much that when preparing slides many years ago, I typed it. Yes. So this little red thing is our attempt to practice orthogonality relation. Right? So each term has m, then something, then another wave function. Bra, cat, right? These coefficients and time derivative coefficients are not functions. They are not subject. The derivative, since eigenfunctions do not change over time, the derivative doesn't act on the function. So we can put derivatives outside of this convolution. Right? Derivative outside of the convolution. And here we have the convolutions. M times 1, m times 2. And here we have matrix elements. Matrix element of Hamiltonian mh1, mh2. So this is a general equation, which is correct, but boring, and I wouldn't mind if you hate it, because it tells nothing. But if we plug specific values for m, it will be hopefully a big brightening of the brains. BBB.
Yeah, big brightening of the brain.
We're classifying.
So if m equals 1, then when it was m1, it becomes 1. When it was m2, it became 0, right? Agree?
Yes.
And then we have 1h1, 1h2. So 0 means that instead of line of all coefficients, we parse only one out of them. So before we had all the coefficients at the left side of the equation, now we have only one. Now, if m equals 2, wherever we have m1, we have 0. Wherever we have m2, we have 1. Again, we have only one coefficient. So we parse only one expansion coefficient out of all of them. Okay? And now on the left, in these two equations, we have time derivative of each individual expansion coefficients. On the right, we have combinations of matrix elements of Hamiltonian and expansion coefficients. Now, let's see, here is C1, C2, C1, C2. So we can identify it as a row by column rule. So if you look on these two connected equations, we can come back. So here is a C1, C2, and it can be considered as row by column. This row by this column. So C1, C2 can be taken out of bracket as a column vector. And we arrive to where we need to be. Okay? So to see how the expansion coefficients C1, C2 go over time, we need matrix elements and the coefficients themselves. So it is what typically H11, H22 are just energies. If there is no light, then 1, 2, 1 are zeros. So it is what we got. Yes! Meeting is done. Have a nice weekend. I bring my apologies that you need to do homework, but it's the nature of academic activities.
Yeah.
Yeah, we understand.
Yeah.
Okay, have a